Well, hello again, everyone. Welcome to our discussion of section 8.3, where we will continue our discussion of polar coordinates and trigonometric functions. So here, in this case, we will begin our discussion of just the basic complex numbers that we recall from Math 126, where we briefly, in one section, we covered complex numbers. So I'll just do a refresher of that material. And then we will dive into polar complex numbers, what they look like and how we can use them in our calculations. And then number two, we will cover multiplying and dividing polar complex numbers. And then we will discuss raising polar complex numbers to a power, also known as de Moivre's theorem. And of course, we will also talk about the inverse of polar complex numbers. And finally, we will look at how to take the nth root of, or take the third root, or second root, or fourth root of a polar complex number. Okay, so having said that, let's just do a quick refresher of the complex numbers in general and how they plot on the XY coordinate system. So a complex number is expressed as z equals a plus bi. So in this case, we call this piece, or a, the real part, and b, not bi, just b, as the imaginary part. So in Math 126, my students often think that bi together is the imaginary part. No, b, this number, whatever it is associated with this I, which is the imaginary indicator of this complex number. So this b, by being associated with I, is the imaginary piece of this complex number, but not bi, just b. Okay, so let us just do a quick example on this. So suppose we want to graph this complex number, z equals 7 minus 3i. Okay. And find its modulus. So, and you may have forgotten about this from previous courses like Math 126. But in this section, we will be dealing with it quite a bit. Okay, so before we begin to do the graph of this, I want to just say that, recall that the modulus of a complex number is as follows. So if we have z equals that, then this would be absolute value of z equals A. So in this case, A is 7, B is minus 3. So we have A squared plus B squared. So square root of A squared plus B squared. In a second, you'll see why this looks like. If you think this looks like the Pythagorean theorem, you're right, but in a few minutes, you'll see why. So that's how we calculate the modulus of a complex number. Okay, then to graph this, first of all, we can do, I'll get my ruler here so I can make better drawings. Okay. Like that. So this horizontal axis will be called the real axis, or the axis where we can plot the A part, and the vertical axis is the imaginary axis. So this is imaginary axis, and this is the real axis. So x, y are now real axis and imaginary axis respectively. Okay, so now we know that A, or the real part, is 7 in this case, right? So let me write that down. We have A equals 7 and B equals minus 3, right? So let's increment 1, 2, 3, 4, 5, 6, 7, like that. And minus 3, that would be along the imaginary axis, right? Because that is associated with the I. So 1, 2, 3. So that's negative 3 increment along the imaginary axis. So that point we're looking for is here, roughly in this spot. Okay. All right. So now the modulus, which has this formula, is easy to calculate because we know what A is and what B is from the original complex number. So let's calculate that. We have absolute value of Z equals square root of 7 squared plus minus 3 squared equals 49 plus 9 equals square root of 58. Like that. Okay. All right, so this was just a reminder to what complex numbers look like, what is a modulus, how do we graph them, and how do we find what A and B are, what the real and imaginary parts are. Okay, so now, moving forward, now we will get to polar form of complex numbers. Okay, I will begin with a couple of graphs. Visually, we should have a visual sense of the polar form versus the original form of a point, or coordinates of a point within the coordinate system, whether it's polar or the old XY or rectangular coordinate system. So let's do a couple of figures, one here and one here. On the left, I'm going to make this the graph for the complex number. And on the right, I'm going to make this a graph of a point within the rectangular coordinate system, like that. Okay. So this is the complex coordinate system, and this is the rectangular coordinate system. Okay, therefore we will call this axis the real axis, and we will call this vertical axis the imaginary axis, and we will call this x, and of course this will be y. So now suppose we have some angle drawn, let's call it theta, and so something like that. I will draw it in the first quadrant, like that, and with a point at the end of it. And we have some angle, let's say the same thing within the rectangular coordinate system. So we want to identify that point within each coordinate system, right? Within the rectangular and within the polar coordinate system. And this is theta, and this is theta. Okay, so now we will, let's draw a vertical line or dashed line for this one, and also for this one, for the rectangular coordinate system. So I mainly wanted to draw this because we're now going to look back at the right triangle. If you thought about that ahead of me, that you are correct. So we're alluding to the old right triangle and its connection with trigonometric formulas. Okay, so here on the complex side, the coordinates of that point would be identified as A comma BI, right? A, of course, is being the real piece of this, so that would be A, and B would be this distance along the y-axis, right? That's that. Now in the rectangular coordinate system, we have, of course, x, y, right? We know that. And so x being this distance adjacent to the theta angle, and y being this vertical distance along the in the direction of the y-axis. But we also learned last class, or in last lecture, I think it was 8.2, that x and y are equivalent to r cosine theta, and y is equivalent to r sine theta, right? We could do a very quick test of this if you forgot. You can do a quick test. Sine of theta would be the opposite divided by the hypotenuse. I should not forget to label this hypotenuse as r here and also r here, the distance r. Okay, so if the sine of theta is y divided by r, right, then y is equal to r sine theta, which is what we have here. By cross multiplying, we can get that, right? And if the cosine of theta is equal to the adjacent side divided by the hypotenuse, then adjacent divided by hypotenuse is x over r. That would be cosine theta equals x over r, and then you can solve for x by cross multiplying. X is equal to r cosine theta. Therefore, we have that. But we discussed that. I'm not drawing that or deriving it here again. We discussed this in section 8.2 or 8.1, one of the two previous sections to this. Okay, what else do we know about the rectangular coordinate, the connection between the rectangular coordinate system and the trigonometric functions or polar coordinates? Well, we also knew that tangent of theta is equal to the opposite side to this angle divided by the adjacent one, right? So y divided by x. Or you could say tangent theta is equal to sine of theta divided by cosine of theta. But of course, that'll be useful, that relation formula or relationship will be useful in some other setting. In this setting, given the right triangle we have, it's better to write it as not as sine divided by cosine, but as y divided by x. Okay? So now that we have set up these two different systems, and I've kind of mixed the rectangular coordinate system with the polar coordinate system here, then let's draw a connection between them. Let's compare these two setups or systems with each other. So we will compare. Oops, the lens just dropped down. Let me fully fix that. I think that's better. So comparing two sides, right? Comparing this side and this side, we have A equals r cosine theta, right? A equals r cosine theta. So let's write that down. A equals r. Let me move this up. Hopefully I can fit all of this on the screen at the same time, like that. So r cosine of theta. And what about B? B is r sine theta, right? B is equal to r sine theta. Like that. So what else do we know? The modulus on this side, given A and B, so we have, okay, from here, I want to draw an arrow to make this clear, and an arrow from here to make this side clear. Okay, on this side, we know that the complex number could be written as, I need to move this up, otherwise I'll be off the screen. Z equals A plus BI, right? We know that about complex numbers. Okay, so on that side, we can write this as Z equals, because we just showed A is equal to R cosine theta, or equivalent to it, and B is R sine theta, right? We just did that by comparing these two figures, these two settings, these two coordinate systems. Okay, so this will be R cosine. I'm just replacing in A and B with these two equivalents from the polar coordinate system. R cosine theta plus I R sine of theta. So I just replace B with its equivalent, R sine theta. And I put I in front because that's how your book writes this, and I want to be consistent with your book. But basically, what are we saying? We're saying that I has this imaginary coefficient, R sine theta. Okay? So, but now R and R can be factored out, right? So this is important, so I'm going to switch to red color, red ink. Factor out R, what do we get? we get r times cosine of theta plus I sine of theta. And here, with this formula, you have the polar form of a complex number. So this is the polar form. Number. Okay. On this side, what you have a formula that will come in handy for both sides, for this system and that system, and this is that formula. And I'm going to box this one as well. So R equals absolute value, and this is the modulus, equals square root of a squared plus b squared, right? So these three formulas, that one, this one, and this one, these three are going to be critical in this whole section. We want to remember these and apply them in each situation. And of course, this R, the modulus being absolute value of z equals square root of this, I promised you that I would show you that this has to do with the Pythagorean theorem, right? R is equal to square root of a squared plus b squared. Square root of a squared plus b squared, which is what we have here by Pythagorean theorem. Okay, so now that we've talked about that, let's get into some examples of applying these. But before that, I saw an example in the book. I wanted to, just in case you come across it and you say, well, what is this and how do I graph this? I wanted to do one example before we do examples involving the polar form of a complex number. So here's that example, just a quick mention of it. So we want to sketch the set, this set, z equals a plus bi, such that a greater than 1, that's the real part, being greater than 1, and b, that's the imaginary piece, being greater than 1. Like that. Okay? And we want to sketch this set in the complex plane. In the complex plane. Okay, it's an easy graph to draw, but I thought this might puzzle some of you how to draw that. That's just setting condition or two conditions on the values of the real and the imaginary piece of this complex number. That's all. So if we have the real axis and the imaginary axis here, let's say that this is 1, and that would be along for B, and then let's say this is 1 along the real axis, and let's put a hollow circle here and a hollow circle here. 1, and then I'm going to draw some dashed line, because the graph of this complex number cannot include a or anything less than a. It can only include something greater than a. And this, I will do another dashed line here. Let me call these with names they should have, which is this one, let's call this B, let's see, B equals 1, that's that line. So we want something greater than that. And this vertical line, let's call that A equals 1, right? That dashed line. So to graph that, we want this region I will use my thicker marker for that. So this is that region, not including the dashed lines. All of that region. Okay, we're staying that. So that's the graph of that, a rough graph. Because we can go off the page, off this classroom, off campus, this goes on forever. Okay, so that's the graph of that. Okay, now we're going to use these formulas that we learned about. Let me or this one, these three, right? The modulus, the formula for modulus, the polar form of a complex number, and tangent theta equals y over x, or b. If you translate it to this figure, it would be b over a, right? Because it's tangent theta is y over x, or b over a. So if you know b and a, you can calculate tangent of theta. All right. Suppose we want, in this example, we want to write the complex number minus 3 square root of 3i, that complex number, in polar form, of course, right? In polar form. Because right now it's just in the form of a basic complex number. We want to convert this to polar form. And with argument theta between, we want that angle to be between 0 and 2 pi. 2 pi. Okay, so let's see what we have here. We know the current form is as follows. So the current form is equal to z equals minus 3 square root of 3i. And we need polar form, which is z equals r cosine of theta, comma I sine theta, right? We want that form. So if we are to transition from here to here, what are we going to need to have? Look at this. What do we need to have in order to transition from here to here? Okay, so we're going to need, at this point, we have A and B, right? What is A in this case? Do you see what A is? A is minus 3. What is B? What is B in this case? It is minus 3 times the square root of 3. So we have that. To transition to the polar form of that complex number, what do we need? We need if you guessed R, you're correct. We need R. We don't know that. What else do we need? We need theta, right? We need theta. So we're going to need those two in order to transition from this form to that form. Now, given what we have, how can we find R? Well, let's remind ourselves what the tools we discussed on the previous page. R, if you have A and B, R can be found using the modulus formula. R is equal to absolute value of Z, that's just a different notation for R, that's all, is equal to square root of A squared plus B squared. Okay, so let's find R. First one. So in our case, R is equal to absolute value of Z equals square root of A squared, so minus 3 squared, plus B squared, minus 3 square root of 3 squared. All right? So then R is equal to square root of 9. Now we have to be careful here. Minus is being raised to an even power, so it cancels out, so it becomes positive. 3 squared is 9. Square root of 3 squared is 3, just 3. This 2 cancels the square root of 3. So we get, once again, we have positive, not negative, after we distribute this power. Then 3 squared is 9. Square root of 3 squared is 3. So 3 times positive 9 is positive 27. Altogether, this is square root of 36. Therefore, R is equal to 6. Right? So we have that. Let's see. What do we do with theta? How can we find theta? Well, let's bring back that previous slide. We do have a formula that says tangent of theta equals y over x. But in the complex coordinate system, y is b, x is a. So tangent theta is equal to b over a. Let's calculate it. And I'm going to just do so they don't mix. So we know that tangent of theta equals b over a, or y over x, and then therefore tangent of theta equals b, which is minus 3 square root of 3, divided by a, which is minus 3. So this will cancel, the negative 3 and negative 3 cancel out. Tangent of theta equals square root of 3. So we have, well, just about, not yet, but we're almost close here to finding theta, right? But we have r. So this tangent of theta equals square root of 3 looks familiar, doesn't it? This square root of 3, where have we seen this before? We have seen it in the special table of trigonometric values. Remember this? All these helpful reference angles that have been helping us all along? Okay, so for tangent, where does square root of 3 appear? Again, eventually, if not already, you will memorize these. But you don't need to memorize all of this, because as long as you remember the sine and cosine, you can derive all these from them, because tangent is sine over cosine. Cotangent is the opposite, is cosine divided by sine. Secant is the reciprocal of the cosine. Cosecant is the reciprocal of the sine function. So you can derive the rest if you know these two columns. And these are not too bad of numbers, and one can easily remember them. So in the tangent column, we have square root of 3 for pi over 3 or 60 degrees. Right? So we know then that theta is equal to pi over 3. Let me move this up. Okay. So now we have that. And this, okay, so now we have the two pieces r and theta that we're going to need to write down the polar form for this original complex number. Okay, so let's do that. R times cosine theta, comma, I sine theta. So we have z equals 6 times cosine of pi 3, comma, I sine of pi over 3, like that. Okay. So we're not going to calculate these quantities, right? We're not going to say 6 times the square root of 3. No, we're not going to do that. This is the polar form of the original, so we're going to leave it like that, as it is. We're not going to simplify this. Okay, so let's see. So let's see how we can multiply and divide complex numbers. So we've discussed polar complex numbers, what they look like, and how to go from a basic complex number to a polar complex number. That was this exercise was all about. And next, we're going to talk about multiplying and dividing polar complex numbers. Okay. Or multiplying and dividing polar complex numbers. Okay, so let's jump right into the formulas. Given that we have two polar complex numbers, Z1 and Z2, and here they are. We have Z1 equaling R1 times cosine of theta 1 plus I times sine of theta 1, right, given that, and Z2, it'll be R2 times cosine of theta 2 plus I sine theta 2, given that we have those two polar complex numbers. Then these are the formulas for multiplying and dividing those two numbers. So we have Z1, Z2, that's when we multiply them. We have R1 times R2, right? Multiply the moduli, modulus for modulus R1, modulus R2, multiply them. Then multiply those, the result, by cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Okay, so we have that formula for multiplying two polar complex numbers. And then for dividing two polar complex numbers, we have the following formula. So Z1 divided by Z2 equals R1 over R2 cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. And of course, given that z or z2, given that z2 is not equal to 0, the measure of that. Okay, so there is definitely a pattern or easy way of remembering these two formulas. So for multiplying two polar complex numbers, multiply their moduli, and then cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Okay, and then for the division, we simply divide the moduli. Z1, if Z1 is being divided by Z2, then R1 is divided by R2, and the sign in between here changes to minus, from positive to minus for the division one. Okay, so let us use these in an example. So given the following polar complex numbers, and here they are, Z1 equals cosine of pi over 4 plus I sine of pi over 4, and Z2 equals cosine of 3 pi over 4 plus I sine of 3 pi over 4. And given that, then the solution, so given the following polar complex numbers, we want to find the product Z1, Z2 and the quotient Z1 over Z2, and we want to express the final form, the final answer in polar form. So we don't want to simplify it beyond that. Okay, we want to keep the answer in polar form. All right, so here's our solution. So recall that the formula for multiplying those two is as follows. That Z1, Z2 is equal to R1, R2 times cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2, right? That's the formula we just introduced. Recalling that, then the R1, R2 in this case, so let's see, we have the modulus of this is just 1, right? The coefficient, the r in this case is 1. The r in this case is also 1. So 1 times 1, so let me write that down. So r1 equals r2 equals 1. Right? Here we have the complex, polar complex form of a number, r1 and r2. Compare that with these. The r is equal to 1, right? The theta for z1 is pi over 4. The theta for z2 is 3 pi over 4, but r is 1. So r equals r2 equals 1. Therefore, r1 times r2. Therefore, r1, r2 is equal to 1. Okay? So then 1 times all of that. So let's write that. We have z1, z2. We'll move this up a little bit. Well, like that. I still want to show z1 and z2 on the screen. Okay, so that much. So then cosine of theta 1 plus theta 2. Theta 1 is pi over 4. Theta 2 is 3 pi over 4. So we have pi over 4 plus 3 pi over 4 plus, of course, I sine of the same thing. Pi over 4 plus 3 pi over 4. Right? Like that. Okay. So that's nothing. All right, so we can then add these two together. Then z1, z2 equals cosine of, this would be 4 pi over 4, right? If you add these, they already have common denominator. 4 pi over 4, and then 4's cancel out, we end up with cosine of pi. Okay, and then plus I sine of the same thing, pi. Okay, so here they wanted us to, we could simplify this. Cosine of pi is -1, sine of pi is 0. So we could just write z1 times z2 equals -1. But they wanted us to express the final answer in polar form. So I'm not going to reduce this. I'm not going to simplify this. If it didn't say express the final answer in polar form, yes, I would write z1, z2 equals -1. But because that's what they want us to keep the answer, final answers as, I'm going to stop there for multiplying those two numbers. Okay? In the homework, online homework, it might ask you to take this, to simplify the answer as far as possible. In which case you would write z1, z2 equals -1. Okay, so we did the multiplication. Let's do the division piece and recall for the division. Recall that z1 divided by z2 was equal to r1 over r2, which is 1 in our case. 1 over 1 is 1, times cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. Okay, that comes from that, with condition that z2 cannot be 0. Okay, so let's plug in r1 divided. So r1 over r2 is equal to 1 over 1 equals 1. We know that. Therefore, z1 over z2 is equal to cosine of pi over 4 minus 3 pi over 4 plus I sine of pi over 4 minus 3 pi over 4. Okay. So let's simplify this, but keep it in polar complex form and not simplify it beyond that. So z1 over z2 is equal to pi over 4 minus 3 pi over 4, that would be minus 2 pi over 4, or minus, after simplifying, minus pi over 2, right? So cosine of minus pi over 2 plus I sine of the same thing, minus pi over 2. So recall that, let me write this down here. Recall cosine of theta is even. Thus, cosine of minus theta equals cosine of theta. Recall that sine of theta is odd function. That's even odd function we talked about several sections ago, right? Thus, sine of minus theta, which would be this case, is equal to minus sine of theta. Remember that? So then let's simplify this according to these rules for even odd functions. So we're going to have z1 over z2 equals cosine of pi over 2, right? Because cosine of a negative number equals cosine of that same number in positive form. So that's what happened here. And then for the sine, because it's odd, so sine of negative theta, or sine of negative pi over 2, is equal to minus sine theta. So minus, the positive becomes minus I sine of pi over 2. And we keep it like that. Let's not, because cosine of pi over 2 is 0, we know that. And sine of pi over 2 is 1. And we don't want to go beyond this. This is the polar complex form which we were asked to give our answers in terms of. Okay. So let's move forward to formula that is used when we raise a complex number to some power, and that is called the de Moivre's theorem. So let's look at that. I should add here, guys, a polar complex number, not just a complex number, but a polar complex number to raising a polar complex number to some power n. Let's call it n, and this is called the de Moivre's theorem. I'm not so, this name of this theorem is not that important, but if you see it in somewhere or in this book, that's what just it refers to. It refers to this formula for raising a polar complex number to some power. Okay, here is that formula. If we have a polar complex number z equals r times cosine of theta plus I sine of theta, if we have that, for any integer power integer power, let's call it n, because that's what your book calls it, with the letter lowercase n. Then we have this formula. So we have z to nth power equals r to nth power times, so the modulus raised to nth power, and then the argument is the argument theta is multiplied by this power. So cosine of n theta plus I sine of n theta. Okay, and this is our formula for that. Okay, so one thing I should introduce in same area as this is the multiplicative inverse of a polar complex number. What does it look like? And because that's important if we ever have to multiply a number by its inverse, if we want to multiply a polar complex number by its inverse, but also because the inverse of this polar complex number will have an integer power equal to -1. So in that case, n would be -1. So that topic falls in the same category as this topic of the de Moivre's theorem, or formula for raising a polar complex number to a power n. So that formula is that. So that would be a quick note here. And I will actually attach it to this one. So note, for a non-zero is denoted by z inverse, or z to -1. That's just a labeling. And such that z times z inverse is equal to 1. So multiplying a polar complex number by its inverse is equal to 1. Okay, and here is where this is the formula for finding the inverse of a polar complex number. Z inverse is equal to 1 over r, so reciprocal of the modulus, times cosine of theta minus I times sine of theta. So this formula is just as important as the one we introduced above, and there is a proof for this. But it's beyond the scope of this course. But if you're ever interested, I'll make it available to you. So here, the proof of this formula is beyond the scope of this course. My colleagues who are focused in analysis can show that very nicely, how all of this is derived. Okay, so having introduced these two formulas, let's use them in an example. So in this example, given two polar complex numbers, so two polar, or actually no, actually these are straight complex numbers, so not yet. So given two complex numbers, z1 equals 5 plus 5i, and z2 equals 4. So this one only has real part. It doesn't have an imaginary part. Given that, we want to find z1 and z2 in polar complex forms, or in polar complex form, and calculate the quotients z1 over z2 and z inverse, i.e. 1 over z. Okay, we want to do that. Okay, so in this case, we have, what do we have? We have for z1, so here's the solution. I don't think I'll be able to fit all this solution on one page. So I might have to continue on another page after this. But so what do we have for the z1? So for z1 equals 5 plus 5i, we know that a is equal to 5 and b is equal to 5 as well, right? So for z2 equals 4, there is no b, so a is equal to 4, or b we can say is equal to 0. Okay, this is important because for transition to polar complex form, we're going to need two variables, right? What are those two variables? You remember? There's r, and the other one is theta. Okay, so for finding the polar complex form for this one, for z1, so polar complex form for z1. Okay, we have r equals square root of a squared b squared. All right, let me move this up. And so 5 squared plus 5 squared would be equal to square root of 50, or equals 5 square root of 2. That's r for z1. What about the theta? So we need that too. So we know that tangent of theta is equal to b over a, or 5 over 5, or 1, right? So this looks familiar, right? Tangent of what angle is equal to 1? It's pi over 4, or 45 degrees, right? So theta, in our case, So here r is equal to 5 square root of 2, and here theta is equal to pi over 4. Now we can write the polar complex form for z1. So z1 is equal to r, which is 5 square root of 2 times cosine of pi over 4 plus I sine of pi over 4. So we're not going to simplify this. They asked us to find the polar complex form for z1. There it is. Okay, for z2, so polar complex form for z2, and so r, notice that for z2, a was equal to 4, b was equal to 0, right? So r would be a squared plus b squared. So it'll be 4 squared, or, and then take the square root, it would be 4. So we have r is square root of 4 squared plus 0 squared. Then r is equal to square root of 16 equals 4. So r is equal to 4. That's for z2. How about theta? So we know that tangent theta of theta is equal to b over a. In our case, in z2, b was 0, a was 4. So 0 divided by 4 is 0. Okay, so the tangent of what value, what angle is 0, 0, right? Tangent of 0 degrees or 0 radians is 0. So theta is equal to 0. Okay, so now we can write the polar complex form for z2. z2 equals r, which is 4, times cosine of 0 radians, 0, plus I sine of 0. Okay, and we'll leave it like that. Okay, so now that we have the polar complex forms of z1 and z2, they're asking us to calculate the quotients z1 over z2 and the inverse of just z1. So I need to make a correction here. When I wrote the statement of the problem, this should be z1, not z2. So we're just going to find the inverse of z1. Okay, like that. That one. The inverse of that. Not, or inverse in polar complex form, not that one. Okay, so let's carry out this one, z1 over z2. Let's divide these two polar complex numbers by each other. We have a formula for that, right? So calculating z1 over z2. Okay, the formula we had was divide the moduli. So divide 5 square root of 2 by 4. Let's do that. I think I forgot. I just noticed it in my problem statement, guys. So I forgot that we're also finding the product, not just the quotient, but the product. So we're finding 3. Once we find the z1 and z2 in polar complex form, we want to calculate the quotient z1 over z2, that, and also the product. So let me quotient this and calculate. I'm going to insert that here. Calculate Z1, Z2. Calculate the product Z1, Z2. Sorry about that. So it's there. So let me then, before we get to the quotient, let's calculate the product Z1, Z2, and we'll go back to that slide again. And so this would be 8, and then I will, for the quotient, this will be page 9. I'm correcting this so when you download these notes, or if you download these notes, they're in correct order. Okay, so for this one, we want to calculate the product Z1, Z2. Okay, so we already have Z1 and Z2, and I better write these on the same slide because I want you to see this on the screen. So we know that we already have. This is better than I think, going back to slide. So we have Z1 equals 5 square root of 2 times cosine pi over 4 plus I sine pi over 4. We have that. And then Z2 was 4 cosine 0 plus I sine 0. Okay, we had that. So if we're multiplying these two, then the moduli, the 5 square root of 2 and 4 get multiplied by each other. So Z1, Z2 is equal to 5 square root of 2 times 4, all of that times cosine of 0 plus pi over 4, or pi over 4 plus 0, makes no difference. Pi over 4 plus 0, plus I sine of, I sine of pi over 4 plus 0. So let's simplify this, and we have Z1, Z2 equals 20 square root of 2 times cosine of pi over 4 plus I sine of pi over 4, like that. Okay. So we can, I'm going to leave the answer in polar complex form, but if we have to simplify this, if a problem says simplify it as much as possible, certainly then we can do that, right? Because this is cosine pi over 4 is square root of 2 over 2. And sine of pi over 4 is, again, square root of 2 over 2. When I come to think of it, though, it doesn't say keep the final answer in this problem. It doesn't say keep it in polar complex form. So we can continue. Let me continue, actually. So in this case, you have both included in the video. So continuing, we have, so that's the polar complex form, if you want to keep it that way. And then simplifying further, we have cosine of pi over 4 is square root of 2 over 2. We have that here, right? We have that in the table of special trigonometric values. Cosine of pi over 4 is square root of 2 over 2, and sine of pi over 4, or 45 degrees, is also square root of 2 over 2. Okay. So that, and then plus I sine of that is also square root of 2 over 2. Okay, and then we can distribute and simplify. So we have 20 square root of 2 times square root of 2 over 2 plus I 20 square root of 2 over times square root of 2 over 2. Just distributing this to both terms. What do we have? We have square root of 2 times square root of 2 is just 2. 2 and 2 cancel out. We get 20 plus the same thing here. Square root of 2 times square root of 2 is 2. 2 and 2 cancel out. We get I 20 or 20I plus 20I. And then, of course, 20 can be factored out. So we have Z1, Z2 equals 20 times 1 plus I. So if we don't want to, if your problem says leave your answer in polar complex form, this is what you leave it at. If it says simplify your answer as far as possible, this is what you conclude with. Okay, so we have the product completed. Now let's go back to what I was going to do, which was calculating the ratio of those two, Z1 and Z2, which is this slide, all right? So let me just write down Z1 and Z2 again, so we can look at them on the screen as we apply the formula. So Z1 is or was 5 square root of 2 cosine pi over 4 plus I sine pi over 4, and Z2 was 4 times cosine of 0 angle plus I sine of 0 angle, right? So in the division, the moduli are divided. So we have Z1 and Z2, so Z1 divided by Z2 is equal to 5 square root of 2 over 4, all of that times cosine of pi over 4 minus 0 plus I sine of pi over 4 minus 0 angle. So let's simplify this. We have Z1 over Z2. And then I'll box this and then I'll simplify it more. So you have both forms. So it'll be 5 square root of 2 over 4 times cosine of pi over 4 minus 0 is cosine of pi over 4 plus I sine of pi over 4. So we have I times sine of pi over 4. So that's one answer. If you want to leave the answer in polar complex form, that's the way to do it. This is I. And then, of course, if you want to simplify, we can do that like before. And so let's do that. So we have Z1 over Z2 equals 5 square root of 2 over 4 times so cosine pi over 4 is square root of 2 over 2 plus I times square root of 2 over 2. Like that. So let's see. Yeah, that should be correct, like that. But I want to double check my other slide. Double check with this. And also so yes, that should be correct. All right. And so making sure that I'm applying the formula the right way. Yeah. So it's plus and plus. Okay. Just double checking. And so continuing with this, we have, let's distribute. We have 5 square root of 2 times square root of 2 over 4 times 2 plus I times 5 square root of 2 times square root of 2 over 4 times 2. So, all right, so we have, do I want to simplify? Yes, we should simplify. Well, I'll box the final answer. So square root of 2 times square root of 2 is 2, which cancels with this 2 in the denominator. We end up with 5 over 4. So like that, plus the same thing, I times, or 5 over 4 times I. And then, of course, we can then factor out the 5 over 4. So we have z1 over z2 equals 5 over 4 times 1 plus I. Like that. Okay. So we're still not done with what this problem asked us to do, which is find the inverse of z1. Okay, so let's do that. So this is calculating z1 inverse, i.e. 1 over z1. So we want to do that. And I'm going to rewrite what z1 is here again. So z1 is equal to 5 square root of 2 times cosine of pi over 4 plus I sine pi over 4, right? So the formula for finding, it was a pretty straightforward formula. It was 1 over the modulus, so 1 over 5 square root of 2 times cosine of pi over 4 minus I sine pi over 4. But let me bring that slide back. So here is that. So inverse of a polar complex form is 1 over the modulus times cosine theta minus sine theta. So let's do that. And we have z1 inverse is equal to 1 over 5 square root of 2 times, of course, cosine of pi over 4 minus I sine pi over 4. But I don't want to leave it like this because we need to rationalize this piece, right? So rationalizing the denominator of 1 over 5 square root of 2, we have this. We have 1 over 5 square root of 2 times square root of 2 over square root of 2. We have square root of 2 over square root of 2 times square root of 2 is just 2. 2 times 5 is 10. Right? So that now let's plug into this with this. Okay, so we have the denominator rationalized. So therefore, z1 inverse is equal to square root of 2 over 10 times cosine pi over 4 plus I sine pi over 4. Okay, so I'm going to box this, which is in polar complex form, but let's continue and simplify it further just in case. Okay, just in case we're asked to do something like that. Okay, so that is square root of 2 over 2. That is also square root of 2 over 2. So z1 inverse is equal to square root of 2 over 10 times square root of 2 over 2 for that, and then plus, yes, so let me correct an error I have here. So the z inverse, that is minus, not plus, and I have an error here, and that plus should be minus. Minus, and then that minus means that this plus here also should be minus. Okay. So I times square root of 2 over 2, and then now we distribute. So z1 inverse is equal to square root of 2 times square root of 2 over 10 times 2, and minus square root of 2 times square root of 2 divided by 10 times 2, and of course I. So let me not forget to put the I here, right? Distributing this to that, and this I like that. Okay, so simplifying this, what do we get? We get square root of 2 times square root of 2 is just 2. 2 and 2 cancel out. We end up with 1 over 10 minus square root of 2 times square root of 2 is just 2. And then let's see. So did I 1 over 10? That should be correct. That's correct. So so minus I times 2, and 2 cancel out, we get 1 over 10. So let's clean this up, let's factor it out. So we have z1 inverse is equal to 1 over 10 times 1 minus I. Okay, and then we have that answer in fully simplified form. Okay. All right. So moving forward, let's apply. Did we talk about? We did talk about De Moivre's. Yes, we haven't yet applied the De Moivre's theorem. That's when we raise a polar complex number to some power. So let's do that in an example. So in this example, we want to find the indicated power using De Moivre's theorem. Okay, so let's see, we have a couple of these examples. So let's name this part A then. So part A, we have 2 square root of 3 plus 2i 2 raised to minus 5 power. Okay, so recall the De Moivre's theorem, right? So recall that z to n power is equal to the modulus to nth power times I cosine of n times theta. So we multiply the argument theta with n, with this power, plus I sine of n theta, like that. Okay. So maybe I should make these brackets like that, since I have the parentheses here, and also that one. Okay, so that's the De Moivre's theorem, like that. Okay, so what do we need in this case? We need the r and theta, right? We already have the n figured out. So we have a equals 2 square root of 3 and b equals 2, and then we need r, which is a question mark, modulus, right? And also theta is a question mark. Okay, so the connection between these two is pretty straightforward. The r is square root of a squared plus b squared. So let's find that. So we have r equals a square root of 2 square root of 3 squared plus b squared. And then r equals, what do we have? So distributing this, we have 4 times 3, right? Because square root of 3 squared is just 3. So that will be 12 here, plus 4, that's 16. So square root of 12 plus 4, it'll be 16. And so r equals that. So r is equal to 4. Now how about theta? Well, theta, we have this nice, neat formula. Tangent of theta is equal to b over a. Remember that? So tangent of theta is equal to b, which is 2, over a, which is 2 square root of 3. So tangent of theta equals 2 and 2 simplify. We get 1 over square root of 3. Rationalize this. So rationalizing the denominator, we have 1 over square root of 3 times square root of 3 over square root of 3 equals square root of 3 divided by 3. Does that look familiar? And this is tangent of theta, by the way. So tangent of theta. Does that look familiar? Well, let's see. Bringing back the special table of special trigonometric values. For the tangent, do we have square root of 3 over 3? Yes, we do. With which angle is that associated with? With pi over 6, or 30 degrees. So tangent of pi over 6 is square root of 3 over 3, which means we have our theta. Our theta is pi over 6. If we didn't have, please remember, if we don't have that number here in this table, we should use our calculator with the inverse tangent function activated. Okay? All right, so from this, then, theta equals pi over 6. So we have the r, we have the theta, and then we can rewrite that this complex number in terms of a polar complex number. Once we do that, then we can then apply the de Moivre's theorem. So let's see. Do we have yeah, that's good. Okay. So now, knowing this and that, we can actually go directly to use this formula. I'm going to have to write it down here as well because it's going to be off the screen. You're going to have duplication on the same page, but it's okay. At least on the screen, it looks the way it should. So here again is the de Moivre's theorem. Is z to n equals r to n times I cosine n theta plus I sine of n theta. Okay. All right. So let's plug in with. Okay. Now we have everything on the screen. So with r equals 4 and theta equals pi over 6, we can plug in. We have z to n, by the way, was -5, right? I forgot to mention that. N is -5. Okay, so z to -5. Like that, equals r, which is 4, to -5 power times I cosine of n, which is -5, theta, which is pi over 6. So -5 times pi over 6 is -5 pi over 6, plus I sine of -pi over 6. Okay. Okay, so now we can then simplify this. Z to -5 power is equal to 4. This number is according to, well, let's okay, so 4 to -5 power, 4, I'm going to use the caret key there, to -5 power. Do I want to do that? No, it's going to give me a decimal. Let's do it this way. I don't want to write in decimal. I want to keep things in exact form. So I'm going to, because this is 1 over that. This is 1 over 4 to the 5th power, right? So what I'm talking about is this. This quantity is 1 over 4 to 5th power. You can put this in the denominator and change the power to positive like I did. 1, this is the same thing as 1 over 4 to the 5th power. So let's find 4 to the 5th power. 4 to the 5th power. And I'm using the caret key there. 1024. So I want, instead of writing 0.0000 here, I want to write 1 over 1 over 1024. That's better because this is an exact value and it's not in decimal form. So 1 over 1024 and times, now we have the, let's see if I, how did I, okay, so this, let me correct this piece because this is not, it shouldn't be there. And I'm supposed to correct that here as well, guys. So up here in the formula for the de Moivre's theorem, there is no I here. The I, this is the imaginary part, right? So let me correct that. I'm just going to do that. I wish I had a whiteout here. I could just cover it neatly rather than that. Sorry about that. So that, and also here, the real part of this does not have I. So that, and also that. So please ignore that piece of that. Before I post these on Canvas, I'm going to white this out so it doesn't look like this. On the video, I can't help it, but once I get to my desk, I will white out those things. It'll look better on Canvas when I post these lecture notes. Okay, so now cosine of minus 5 pi over 6, I guess I can do a little image here because that's the only place I have left. That angle going in the well, first of all, let's make use of the fact that cosine is an even function and sine is a odd function. So cosine minus 5 pi over 6, because cosine is an even function, is equal to cosine 5 pi over 6. And because sine is an odd function, sine of minus pi over 6 is equal to minus sine pi over 6, 5 pi over 6. So minus I sine of pi over 6, because sine is an odd function. So we have that. So this minus comes out and in front. Okay? So now we have this, I wanted to draw it here, but I think that would make this page very crowded. So I'm going to have to go to the next page. And it's better to do that. So let's see what the measure of each of these trigonometric functions is. Like that. Okay. So 5 pi over 6, in which quadrant is this? It has to be in the second quadrant, because if you had 6 pi over 6, you would be at pi, and this is slightly less than that, so we are in the second quadrant. So let's draw that. And so theta and cosine theta. And then we have the like that. 5 pi over 6 would be that. 5 pi over 6, right? So that's 5 pi over 6. That means, what is our reference angle? What is the what is the measure of our reference angle? Right? The measure of our reference angle is theta r equals pi over 6. Right? And we are, let's remember that we are in quadrant 2. In quadrant 2, so the measure of cosine of pi over 6, we can get that from our table of special triangle values, right? It should be square root of cosine of pi over 6 is equal to square root of 3 over 2. But remember, these are all in the first quadrant. for this problem, we're in the second quadrant. In the second quadrant, the value of cosine is negative, right? So we have to then, that would be minus square root of 3 over 2. So let's write that down. So continuing, we have z to negative 5 power equals 1 over 1024 times that measure is minus square root of 3 over 2. Now here, so minus sine of pi over 6. We can look that up. That's our reference angle, right? The reference angle for 5 pi over 6 is pi over 6. We can look that up. Sine of pi over 6 is 1/2, okay? But what is the sine of it? In the second quadrant, the sine is positive. And we expect it to be, right? The reflection of the reference angle reflection of the reference angle for sine is along the y-axis, and the y-axis in the second and the first quadrant is positive. So we have sine of x positive, sine of x is positive. But for cosine, the reflection of the reference angle is along the horizontal axis, and the horizontal axis in the second quadrant is negative. So we have that. Okay, so we have, here we have 1/2 I, right? Going from here to here. That would be 1/2, and the minus is in front, 1/2 I. Okay, so let's simplify this. And let's distribute as much as we can. This one in the brackets, these terms have a factor of 1/2, right? So let's factor it out. So z to negative 5 power is equal to 1 over 1024 times 1/2, factoring out 1/2, times what's left, it'll be minus square root of 3 minus I, like that, right? And then multiply these two. So z to negative 5 power is going to be 1 over 2048 times that, negative square root of 3 minus I. And this is our final value there. Okay, so we used, what did we do? We used the de Moivre's theorem to find the inverse of, the de Moivre's theorem to raise this complex number to this power, negative 5. In the next example, we will do the same thing, but with a positive power. Okay, let's do that. So suppose we want to raise this complex number, 3 plus square root of 3i to 4th power. Okay, so in this case, we have a, which is 3, b, which is square root of 3, and we need, because de Moivre's theorem is based on the polar complex number form, right? Not on the complex form. So we need to obtain the polar complex form before we can apply the de Moivre's theorem. So we need then r and theta. So we can find r easily by taking the modulus, which is square root of 3 squared plus square root of 3 squared. What do we have? We have square root of 9 plus, that would be 3, no, this is 2, not 3. Okay, 2. So 3 squared is 9, square root of 3 squared is 3, and then we have square root of 12, or that's 4 times 3, right? 4 times 3, which is 2 times square root of 3. Okay, tangent of theta is equal to b over a. Remember that? So square root of 3 over 3. And so, do we remember this? We do, right? Tangent of what angle is, is equal to square root of 3 over 3? It's pi over 6. So from this, we know that theta is equal to pi over 6. Okay, now by de Moivre's theorem, we know that z to n power is equal to r to n times cosine of n theta plus I sine of n theta. We know that. So let's apply it in this case because we have both r. So r is equal to 2 square root of 3. That's from above. R equals that. And theta equals that. So we have z to 4th power is equal to, because this whole thing is z, right? 3 plus square root of 3i is z. So z to the 4th is r, which is that, 2 square root of 3 to 4th power times cosine of n, which is 4. The power is 4, and that's n. 4 times pi over 6. I will simplify this next. Plus I sine 4 pi over 6. Okay, so simplifying, we have z to the 4th. That is, if you raise this power to that 4th power, we get 144 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. Well, we can simplify this further. Let's draw a quick picture for this. So here we have theta, and that will be sine or cosine theta. So 2 pi over 3, if you had 3 pi over 3, you'd be at pi, which would be here. But this is a little bit less than pi, right? Because it's, instead of 3 pi over 3, is 2 pi over 3. So the angle is somewhere here, again in the second quadrant. That is, this angle is 2 pi over 3. So what does that mean in terms of the reference angle? That means the reference angle has to be pi over 3, right? If you convert this to degrees, what would it be? 2 times pi over 3. What would it be in the terms of degrees? We discussed how to convert degrees from radians to degrees and vice versa very early in the semester, right? So this, in this case, it would be 360. So this would be 120 degrees. So the reference angle would be 60 degrees or pi over 3. So we can look that up for cosine, but just remember, we're in the second quadrant, right? So the value or the magnitude of that for pi over 3, we can get cosine of pi over 3, it is 1 over 2, right? So, but this is all in the first quadrant. So we are in the second quadrant where cosine is negative, because the reflection of the cosine of a reference angle in that quadrant is along the horizontal line, and the horizontal line here in the second quadrant is negative. So that'll be minus 1 over 2. And so let me write that down. So z to the fourth equals 144 times minus 1 over 2 plus I sine of 2 pi over 3, sine of 60 degree, or pi over 3, right? So, because that's our reference angle. So that'll be, we know that's, so bring this back. Pi over 3 has sine square root of 3 over 2. But this is in the first quadrant. We are in the second quadrant. In the second quadrant, the sine is positive again, right? Because the reflection of the sine of the reference angle, which is pi over 3, falls along the y-axis. And the y-axis is positive in the first and the second quadrant. So we'll have positive square root of 3 over 2. So plus I times square root of 3 over 2. Okay, I hope this is starting to make sense because it's all connected, the reference angles to this and all these formulas. So then let's factor out 1/2 from these two terms. We'll have z to the fourth equals 144 times 1/2 times minus 1 plus I square root of 3. And finally, here's the last result. 144 divided by 2, we get 72. So z to the fourth power is equal to 72 times minus 1 plus I square root of 3. Like that. So this is just calculating any number of roots, otherwise known as nth roots of complex numbers. And this will be the last topic in this section 8.3. Okay, so suppose we have a complex number given the complex number z equals r times cosine of theta plus I sine of theta and that n is, let's say, it's some positive integer. Then we have this formula for finding the nth roots of, or as many roots of, a complex number, and that the formula is as follows. So So W with a subscript K. This K is critical in denoting the specific root that we're calculating, and I'll have more to say about it in a bit. And R to 1 over n, and n is some positive integer, times cosine of theta plus 2k, that's the same k, 2k pi over n plus I sine of theta plus 2k pi over n. Okay, and here k is any integer, positive integer, 0, 1, 2, all the way to n minus 1. So if you're looking for 5 roots of some complex number, 5 roots, right? So this has, the k has to go from 0 to n minus 1, because we're counting k equals 0 in this formula as one of those roots. So with k being 0, 1, 2, 3, 4, that's 5 roots, right? 0, k equals 0, k equals 1, k equals 2, k equals 3, and k equals 4. That's calculating this formula 5 times, beginning with k setting at 0 and all the way to 4. So that's why if you're looking for 5 roots, this k should be calculated from 0 to n minus 1, because we're calculating 0 at k equals 0 as the setting for one of those, for the first root, so to speak. Okay, so if you're looking for 7 roots, you increment k from 0 to 6, because counting 0, k equals 0, you're going to have 7 roots. Okay, if you're looking for 10 roots, the k would have to increment from 0 to 9, or 10 minus 1, which is 9, because calculating 0, k equals 0 as one of those roots, then k equals 0 to 9 will give you exactly 10 roots. That's why. And the other thing is that this formula is in radians. Your book gives you the same formula in degrees as well. So I'm going to do that also. So this is the formula in radians, or, so we have, or the same formula with the same rules, but instead of pi here, we will have, instead of 2 pi, which is 360 degrees, right? Instead of that, we will have 3 theta plus 360 degrees k over n. Just replacing 2 pi here and here with 360 degrees, which is this one. (360 k over n plus I sine of theta plus 360 degrees k divided by n. Okay, so this is that. Let's box it. And the same rules apply here. So this is the formula in degrees, and what we said about k also applies here. So if you're looking for 4 roots, k would increment from 0, 1, 2, 3, or n minus 1, because if n is equal to 4 for 4 roots, then k would have to increment from 0 to 3, because that's going to give us 4 roots, right? K equals 0, 1 root, k equals 1, another root, k equals 2 gives us another root, and k equals 3 gives us another root. Okay. And I will write this down also for your notes. So note that the value of n determines how many roots must be calculated. Which is n minus 1, right? Because k starts at 0. K equals 0 is the first root that will be calculated. Okay, so we talked about that. Then also let's say something about WK here. That's also a node. So WK equals the specific root W0, W subscript 1, W subscript 2, on and on. That is being calculated. Calculated here. So let's add something else. These are just to clarify what these formulas are doing. That's all these notes. So if WK So if WK is a complex number, which is a root of complex number Z, see, so the roots of complex numbers are complex numbers themselves. The roots are themselves a complex number here. That's what this is saying. So if that is a complex number, which is a root of the complex number Z, then we can say this. We can say that WK to n power is equal to Z. All right? So each of those roots that we're finding, if you raise each one to n power, suppose if we found 5 roots, then if we raise each of those individual roots to 5th power, we should get the original complex number, keeping in mind that WK itself is a complex number as well. And of course, this raising a complex number to nth power makes use of the de Moivre's theorem. Remember, we talked about that. That's the formula we use to raise a complex number to some power. Okay? So then let's say something about, because these formulas have a graphical interpretation as well. Let's say something about the graphical interpretation of the roots that result from this formula. So if we graph all those roots that we're finding, if we graph all roots of z, when graph all roots of z are spaced equally on a circle of radius, this is very, very important, of radius r to 1 over n power, 1 over n power. So this is the radius. So let me bring back this formula. So this formula, that what you have outside of this bracket, r to 1 over n power, is the radius of that circle. And each of the roots we're finding by incrementing k to 0, 1, 2, and so on and so forth, each of those roots will be plotted equally distant from each other on a circle. Okay? So that's the geometric interpretation of this formula. This whole thing is the radius, not just r. r to 1 over n is the radius. And the individual roots that we find by incrementing k to 0, 1, 2, 3, so on, are going to plot at equally distant points on a circle. And we'll see an example of that. Okay, so I guess this next node is kind of obvious once you get to use the formulas, but I think it's better for you to have it in these notes rather than not have it. So I'm going to write it down. Of a complex number, the first root is theta over n. And when I said it's obvious, it's because if k equals 0, right, k equals 0 gives you the first root, always. K equals 0 gives the first root, always. So if you substitute for k with 0, then that term 2k pi drops out. You end up with theta over n here and theta over n for the sine function. So that's what that note is saying. It's saying that the first root is that, and incrementing k from 0, 1, 2, 3, and so on, that can be used to repeatedly add 2 pi over n to get the argument for each of the successive roots, for each successive root. Okay, so that means if we go back to this, so beyond k equals 0, if k equals 1, so you'd have theta plus 2 pi over n. If k equals 2, then you'd have theta plus 4 pi over n. So repeatedly we're adding multiples of 2 pi to theta over n to find each of the successive roots. That's what that note is basically saying. Okay. I'd rather have you in that road in the notes than not have it. So, okay. So in all the examples we've done so far, I grabbed those examples in all the videos from the back of each section problems. So they are not the same problems as the problems that the book solves for you, in the example problems that they solve for you. I intentionally did that because that'll increase the pool of solved examples you have at your disposal, and you can use more examples to study on all these topics. So I've always used examples that are different than the examples that are solved in your book, okay, for that purpose. So you have more problems to look at to get better at this stuff. But this next problem is an exception. For this kind of formula, it's really difficult to find a good problem from the back of the or the end of the section problems. So in this case, I used an example that is solved in your book. So I'll go over that, and when you read that from your book, it's the same example. Like I said, this is very, very rare. I haven't done this so far, but in this case I make an exception because it was difficult to find an example that would be as good as this one. Okay, I could find examples, but they were not as good as this. Okay, so let's go through an example of applying this formula. This is example number 8, at least that's example number 8, page 560 to 561 of your textbook, at least the edition that I'm using now to build up these lecture notes. Okay, so here we're asked to find the sixth roots of the complex number z equals negative 64. And graph the roots. We're asked to graph the roots in the complex plane, okay, for this complex number. Okay, so what do we have? So we have A, which is negative 64. We have B. B would be the coefficient of the imaginary part, right? There's no imaginary part, so B is equal to 0. By the way, all real numbers, in case you're wondering why we're calling this a complex number, all real numbers are complex numbers. They are a subset of complex numbers. So technically, we haven't done that so far, but if you want, you can call a real number also a complex number. But of course, if the imaginary piece is missing, it's just 0. The imaginary part is 0, like this one. Okay, so we have this information from this complex number. And we need, in order to find the 6 roots, we need to convert this to a polar complex number, right? So what do we need for that? We need R value, and we need the theta value, right? Remember those two things? Okay, so finding R is very easy. So actually the solution started from here. So r, or the modulus, as we called it last time, is square root of negative 64 squared plus 0, or b squared. So what do we get? We get 64 again. Positive 64 is r. So r equals 64. Okay, so that's what we have now. Also, we need the theta, right? So how do we find theta? So we know that tangent of theta is equal to b over a, right? So b is 0 in this case over a. So if tangent of theta equals 0, then theta can be equal to 0, can be equal to pi, 2 pi, and so on, right? So I'll just pick you can pick in any one of these. I'll just pick pi to be our theta. Okay, so theta equals pi, and that's what your book did as well. Okay, so we're going to use theta equals pi and r equals 64. Okay, so the polar form of z equals minus 64 is as follows. It's z equals 64 times cosine of pi plus I sine of pi. Okay, using r and then pi as the theta. So now we're applying the formula for WK for n equals 6, right? Then the k value, so k should increment. We're looking for 6 roots. Each root starts with k starting at 0. So to find 6 roots, then the k must increment as follows. As follows. K equals 0, k equals 1, k equals 2, 3, 4, and 5, right? That's this 5 we have to stop because that's 1, 2, 3, 4, 5, 6, which is the number of roots we're looking for. So that's why here in that slide we said that k must be incremented from 0, 1, 2 all the way to n minus 1 to find the number of roots we're looking for. Okay, so we're looking for 6 roots, so k should increment from 0, 1, 2, 3, 4, and 5. Okay, so meanwhile, so this is an important note. Also note, because we're going to use this formula right now, this formula, the one that we just introduced, and that formula begins with this quantity, r to 1 over n power. In our case, r was 64. We found r to be 64, right? R is equal to 64, raised to 1 over n, right? 1 over 6 in our case. So note that 64 raised to 1 over 6 equals 2. Just keep that in mind. So in this formula, wherever we have r to 1 over n power, we're just going to use 2. Okay. So knowing that, then let's find the individual roots. So here is, I want to write down the formula on top of the page so we can look at it as we plug in the values. So here's the formula. WK is equal to R to 1 over n power times cosine of theta plus 2k pi over n plus I sine of theta plus 2k pi over n, and like that. So that's our formula. Now applying it when k equals 0, right? We start from k equals 0, then WK would be W0 equals to 2, remember? So we already calculated 64 to power 1 over 6 is 2. So 2 times cosine of that theta is going to be pi. We chose pi, right? Cosine of pi plus k is going to be 0. So there is just 0, 2k 0, so 2 times 0 times pi is 0 over 6. And then plus I sine of pi plus 0 again because we're using k equals 0. So that term is 0 over 6, like that. So this will be root 0, or that root, or the first root, not root 0, but first root, for which k is equal to 0. It's going to be 2 times, so we have cosine of pi over 6, right? Cosine of pi over 6, like that, plus I times sine of pi over 6. So this parenthesis should have been around pi over 6, but it's okay. It doesn't matter. So then cosine of pi over 6, that looks familiar, right? Cosine of pi over 6 is equal to square root of 3 over 2, right? So therefore, we have 2 times square root of 3 over 2 plus, what is sine of pi over 6? Do you remember? It's right here. Sine of pi over 6 is 1/2. So I, or 1/2 I, then distribute this 2 into this. What do we get? We get the first root equals square root of 3. If you distribute the 2 into this, both terms, we get square root of 3 plus I. So that is the first root. Okay? We are looking for 6 of these. So that's the first root. Okay? So the second root, when k equals 1, we have w with 1 subscript equals 2 times cosine of, now remember this formula? So k is 1 now, so 2 pi. Theta plus 2 pi over 6. Pi plus 2 pi over 6 plus I sine of the same thing. Pi plus 2 pi over 6. Okay. So we have, what do we have? We have 2 times, this is 3 pi over 6 or pi over 2, right? So 2 times cosine of pi over 2 plus I sine of 3 pi over 6, again, is pi over 2. Now we know cosine of pi over 2 is how much? Do you remember? Cosine of pi over 2 is 0. Right? So 2 times 0 plus sine of pi over 2 is 1/2, right? Sine of pi over 2 is 1. So I times 1 is just I. So this one is just 2I. And that is the second root. We're getting there, right? We need 4 more roots to calculate. Okay? So when k equals 2, then we have W2 equals 2 again, this time cosine of pi plus 4 pi divided by 6 plus I sine of pi plus 4 pi over 6 and then W2 is equal to 2 times cosine of 5 pi over 6 plus I sine of 5 pi over 6, like that. Okay? So this is, in which quadrant is this? Do you remember? So if this was 6 pi over 6, we would be at the end of the second quadrant, but this is slightly less than that. So we are in the middle of, somewhere in the middle of the second quadrant. In the second quadrant, what is the sign of the cosine and sine? Well, in the second quadrant, the cosine is negative, the sine is positive. Remember that for cosine 5 pi over 6, the reference angle is pi over 6. And so we have, so the reflection of the reference angle pi over 6 in the second quadrant is along the horizontal line for the cosine of that angle. For cosine pi over 6, it's going to be negative because it's along the negative side of the x-axis. And the reflection of the sine of that reference angle, which is pi over 6, in the second quadrant is going to be along the vertical y-axis, and that's positive. So sine is positive, cosine is negative. Okay, and we already know that cosine of pi over 6, that's being the reference angle, is equal to square root of 3 over 2, and the sine is 1 over 2. So all we have to do is just use those numbers that we have on that table of special trigonometric values, but with keeping in mind that in which quadrant we are, right? So W2 would be for cosine. Cosine, we just saw it's going to be negative square root of 3 over 2 because we're in the second quadrant, right? So square root of 3 over 2 you can get from the table. But the quadrant, this angle 5 pi over 6, it tells you you're in the second quadrant, therefore you have to make this minus square root of 3 over 2. For sine, it's going to be positive, and sine of pi over 6 is 1/2, so we have plus 1/2 I. Okay, so if you distribute the 2, we get W2 equals minus square root of 3 plus I. And that is the third root. Okay, let's find the fourth root. So when k equals 3, then we have W3 equals 2 times cosine of pi, which is theta, plus 6 pi over 6 plus I sine of the same thing, pi plus 6 pi over 6, end of the bracket. Okay, so let's simplify. We have W3 equals 2 times cosine of 7 pi over 6 plus I sine of 7 pi over 6. So in which quadrant is this? Because we know already the reference angle is pi over 6, right? But which quadrant? This is going to be, this 6 pi over 6 would be pi. This is slightly bigger than pi because of 7 pi over 6. So we're in the third quadrant. So in the third quadrant, both the sine and cosine are negative, and they should be, right? Because the reflection of the cosine of a reference angle happens along the horizontal line, and in the third quadrant we are the horizontal x-axis is negative. How about the y? The reflection of the sine of a reference angle in the is along the y-axis. In the third quadrant, the y-axis is negative, so sine and cosine are both negative values. So that we have to keep in mind as we plug in numbers here. So W3, so both of these have to be negative. Cosine of 7 pi over 6, that's going to be negative square root of 3 over 2. And that's going to be plus I times sine of 7 pi over 6 is going to be minus 1/2. Okay, so distribute the 2 into these two terms. What do we get? We get W3 is equal to negative square root of 3 minus I. Right? The 2 and 2 cancel each other out. So we have this as our fourth root. We have 2 more roots to calculate, right? For k settings equal to 4 and 5. So let's do that. Okay, so when k equals 4, then we have W4 equals 2 times cosine of pi plus 8 pi over 6 plus I let's see, yes, plus I sine of pi plus 8 pi over 6, like that, right? Okay, so now W4 is equal to 2 times, so we have cosine of, this will be 9 pi over 6, but let's simplify it as we go along. So 9 pi over 6, that will be 3 pi over 2 plus I sine of 3 pi over 2. Right? So 3 pi over 2, if we were 2 pi over 2, we were at pi, but 3 pi over 2, that's in the third quadrant. So, and what is the reference angle here? It's pi over 2 in the third quadrant. So therefore, let's remember what those values are. For pi over 2, which is the reference angle for 3 pi over 2, the sine is, well, this is for pi over 2, but this is in the first quadrant, right? It's positive 1, the sine of pi over 2. So the sine of pi over 2 is 1 in the first quadrant. We're in the third quadrant, so that's negative 1 for the sine. For cosine, it's just 0. Okay, so we have this first term is going to be 0. The second term is going to be negative 1. So I times negative 1. And if you distribute to that, you get minus 2i. Okay, and that is the fifth root. So let's do the last root, which is the sixth root. When? And that happens when? When k equals 5. All right? So 2 times cosine of pi plus 10 pi over 6. I'm just plugging into the original formula that we have for WK, plus I sine of pi plus 10 pi over 6. So what do we get? We get 2 times cosine of 11 pi over 6 plus I sine of 11 pi over 6. Okay? So which quadrant is this? Well, if we were at 12 pi over 6, which is a slightly bigger angle than this, we would be at 2 pi, right? But this is a slightly less than 12 pi over 6. So we are in the fourth quadrant. Okay, so in the fourth quadrant, the cosine value, which is has to have the sine of the horizontal axis in that quadrant, would have to be positive, right? And the sine, which would have to take the sine of the y-axis in that quadrant, have to be negative. So sine is negative in the fourth quadrant. Right? Let me move this up a little bit. Right? In the fourth quadrant, sine is negative because it has to do with the reflection of the reference angle along the y-axis. And in the fourth quadrant, the y-axis is negative. The cosine has to do with reflection of the cosine of the reference angle along the horizontal axis. And the horizontal axis in the fourth quadrant is positive. So we know this quantity is positive and this quantity is negative, right? But 11 pi over 6 has the reference angle equal to pi over 6. So this would be negative or positive square root of 3 over 2 along the horizontal, which is positive in the fourth quadrant. And this one would have to be negative 1 over 2, which is the case for any angle in the fourth quadrant, because the y-axis is negative in that quadrant. So we have W5 equals 2 times square root of 3 over 2. I'm getting these values from the reference from the table of special trigonometric values. So for pi over 6, cosine is square root of 3 over 2. And for sine, it's 1 over 2. But for sine, we have to be careful because it's going to be negative in the fourth quadrant. Sorry, this should be, let me correct that. So this is going to be negative 1 over 2. That's what I meant to write. I didn't mean to write the sign again. So let's distribute the 2 into the brackets. We have W5 equals square root of 3 minus I. And that is our 6th root. The last root we were looking for, right? 6th root. Okay, so you already have this in your notes that these roots, when we try to graph them, are located around a circle at distance equal to each other. Okay, so let's just draw that. And I'll just make a note here that the 6 roots just calculated are located on a circle of what radius? Do you remember? Radius 2, where did the 2 come from? It came from 64 raised to 1 over 6 power equals 2. Located on a circle of radius that at equal distance from each other. So these 6 roots that we found are going to be on a circle of radius 2 units, and they're going to be at equal distance from each other. So I'm going to draw that here. So this would be the real axis, and I'm a little bit off the screen there. Move it into focus here. Real, and then of course the imaginary axis. And I'll just try my best to draw a circle that is a little bit symmetric. That's as best as I could do it. And then, so we know that this radius is equal to 2, right? This radius, r equals 2. And then our angles were as follows. So where are these roots located? I mean, the W0, W1, W2, W3, W4, 5, all of these roots that we calculated. We need to locate those. So where are they? They are associated with those angles that we had. So here are those angles. We had when k was equal to 0, then theta or W0 was at theta equals pi over 6. Remember that? You can go over the calculations and find these. When we calculated k equals 1, at that point, the second root. So W0 is the first root. W1 was the second root. Happened at theta equals pi over 2. When k was equal to 2, W2, or the third root, was at theta angle equal to 5 pi over 6. When k was equal to 3, W3 happened at theta equals 7 pi over 6. When k equals 4, W4 happened at theta equals 3 pi over 2. And finally, when k was equal to 5, then W5, which is the sixth root, happened at theta equals 11 pi over 6. This last one is the one we did here. 11 pi over 6, right? Pi plus 10 pi, 11 pi over 6. Okay, so we can easily now plot all these roots around this circle. Pi over 6 would be somewhere here, right there. That's 30 degrees. So that's the first root. W1, or the second root, would be at pi over 2. That would be here. That's W1. W2 is at 5 pi over 6. That would be here, which is 5 pi over 6 has reference angle pi over 6 with respect to the x-axis, right? So it would be right across here, here. And that would be W2. So these roots must be equally distant from each other, even though manually I cannot draw it that well, but with a computer they would be at equal distance from each other around the circle of radius 2. Okay, and W3 is 7 pi over 6, and so that should be somewhere here. Like I say, manually I can't draw these that well, but they should be at equal distance from each other. So it would be somewhere there. And then W4 would be 3 pi over 2. So that's exactly that. And 11 pi over 6 would be roughly here. And that is W5. Okay, if you wish, you can draw, lines to these roots, like that, like this, and like that. Okay, this is how we find the roots of a complex number. Okay, with having said that, we have wrapped up this section 8.3. Thank you again for persisting through these videos, and please send me or bring me your questions, and hopefully you can be clear on all this material we covered in this video. Until next time, have a good day, and I'll see you later.